Hi, welcome to Lesson 23D, the Binomial Distribution. The goal of today's lesson is to learn how to use the binomial distribution with probability. So we've been looking at general discrete random variables in the past. Now we're going to be looking at something that's a little bit more specialized. It's going to be connected to sampling with replacement, meaning that the probabilities will not change. And this is, we're going to be looking at the distribution, the probability distribution, associated with the binomial probability distribution. And the key to the binomial is this word bi, meaning two. And the idea of this is there are only two possible outcomes. So when we start talking about probabilities, if you get questions where, or situations where there's only two possibilities, like suppose we say, oh, a group of people are in favor of some sort of decision. So some people are in favor and others, of course, would not be in favor. So those are the two possibilities. Or we could say, say an archer hitting a target, and I'm not much of an artist, as you can probably see, but an archer hitting a target somewhere, and that would be, so he either hits it or he misses it. Okay, so those are the binomial, the two possibilities, either hitting the target or not hitting the target. And so when we do that, when we discuss these binomial situations, we label one as a success and we label the other one as a failure. And I guess the one that we talk about as a success is the one we're most interested in. And it's not necessarily a true success and failure in other aspects of the words. But success is the aspect of the experiment that we're most interested in finding out. Okay? So there's a few things that we have to realize about binomial experiments. And one of them is that there are n identical and independent trials. Okay, so meaning that they're independent, meaning that the probability of one, or the occurrence of one outcome does not affect the probability that the other would occur. Henceforth, the independent. And they're identical, meaning that the probabilities will not change. Hence, the idea of probability with replacement, where the probabilities themselves will not change. So they're identical in that way. And there's some n number of trials. As I stated up here, in terms of success and failure, there are two possible outcomes, and that's it. Okay? You're either in favor or you're not. You either hit the target or you don't. You either turn left or you turn right. Or you either get a head or a tail when you flip a coin. Or a light bulb is defective or it's not. So things like that. It's either one or the other. And so that's the thing that you really have to pay attention to when you get some sort of random practice questions and you're interested in finding out, oh gee, is this binomial? Is this just another one of these other probability questions? If it's a failure or success, there's only two possible outcomes, then it's definitely binomial. I've already mentioned this, but the third thing is the probability does not change. Okay, so from one trial to the next, the probability is going to stay the same, therefore the idea of probability with replacement. And the whole idea of these experiments is to determine the number of successes. Okay, so whatever you choose as a success, that's all you're really trying to find out. You don't care how many failures there are. It doesn't, the order doesn't really matter of the number of successes. We just want to know, out of say 10 trials of, I don't know, 4 objects, how many times will there be whatever we deem as a success, whatever outcome we are looking for as a success. So we're just looking for that, and about the failures we don't really care. Okay? So when we're dealing with this, as you know, as I've been saying, there's either a success or a failure. So because there's only 2 outcomes, then every time you run the trial, there is going to be either a success or a failure. Therefore, the probability that you either succeed or you fail is going to equal 1. So the probability of the success plus the probability of the failure will equal 1. So that's one other thing you can check, just to make sure that those things will add up appropriately. And part of the notation regarding success and failure is usually what we'll do is we'll say that a success is labeled as P, that's lowercase p, and a failure, well, if the success and the failure add up to 1, and the success is P, then a failure will be 1 minus P. And that's how we'll be looking at the probabilities. So let's say, for example, the probability of some sort of success is, say, 2/3. So that's our P. Then, obviously, the failure would be 1 minus P. Therefore, the failure would be 1/3, because it's 1 minus the 2/3. Okay, so that's how we're going to be setting up the calculations for the successes and failures. Okay, so let's say we have some sort of a distribution. We've got some probabilities. Suppose we're using a spinner. There's a spinner. And we see there's 2 large shaded sections and then 2 small unshaded sections. So if we look at each half, hopefully we can agree that each half of this, 2/3 of it is shaded, 1/3 is not shaded. So when you look at the whole thing all together, then obviously 2/3 is shaded and 1/3 is not shaded. So let's say that landing on a shaded section would be a success. So that means that the probability of landing on a shaded section being a success would be 2/3, and therefore the failure would be 1 minus 2/3, which we can just state down here. 1 minus 2/3, which is just 1/3. Okay, so the success is 2/3, and the failure is going to be 1/3. So suppose we spin the arrow a few times, and let's say it's 3 times. Then we can set up this tree diagram here, and we can say that, well, if we spin it around, the possibilities, the random variable x, could either equal 0, 1, 2, or 3. So if we're spinning it 3 times, the arrow could land on the shaded section 0 times, which is fairly unlikely. It could land on it once out of those 3 spins, it could land on it twice in those 3 spins, or 3 times in the shaded section of those 3 spins. So we set up the tree diagram. So on the first spin, there is a 2/3 possibility or probability that it's going to be shaded, 1/3 is going to be not shaded. And after the first spin, we spin it again. There's 2/3 of a probability that it'll land on the shaded section again, and only 1/3 is going to be non-shaded. And then down here we can look at the same probabilities. After it lands on a non-shaded section, we spin it for the second time. It could either be 2/3 probability that the arrow lands on a shaded section, and 1/3 it lands on the non-shaded. And then that continues on. So there's still 2 probabilities from each of those outcomes, shaded or non-shaded. So if we're going to look at x equals 0, so the arrow in those 3 spins does not land on a shaded section at all, we'd follow this branch here. So 1/3 is probability that it lands on a non-shaded section. The next spin, it lands again on a non-shaded section. That's a 1/3 probability. And then another 1/3 probability that it lands on a non-shaded section. Therefore, when we take all those independent events together, those outcomes, we get 1/3 multiplied by 1/3 multiplied by 1/3. So that's 1/3 all cubed, which would give us the probability that in those 3 spins, the arrow does not land on a shaded section. Then if we say it's 1 shaded section or 2 not shaded sections, well, when we spin it 3 times, it could either land shaded and then not shaded, or it could be not shaded on the first spin, then shaded, then not shaded, or the first spin would be non-shaded, second spin is non-shaded, and the third spin is shaded. So when we take all those into consideration, in each one of those, we've only got the success 1 time, and so there is 2/3 probability that it'll land on a shaded region, and 1/3 probability that it'll land on a non-shaded section, but that could happen twice, so that's why we square that. And there's 1, 2, 3 ways that this could happen, so then we multiply that by 3. And then we see, well, what's the probability that the spinner, the arrow, will land on the shaded section 2 times? Well, then we've got 3 different possibilities, 3 different orders, 3 different ways that'll happen. So that's why we're going to multiply this by 3. And we've got shaded, shaded, hence squared. Shaded and shaded is twice there and twice here. So that's why it's going to be squared. And then non-shaded, the probability is going to be 1/3. So all of these calculations come from the tree diagram. So we could do shaded, non, or we could do shaded, non-shaded, or non-shaded and shaded, okay, for these outcomes. And then you just multiply along the branches to find the final probability. And then the final outcome that we could be looking for would be when x equals 3, when the arrow lands in the shaded section all 3 times. So it'd be shaded, 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 which is 2/3 cubed. Okay, so what we can do then is we can add all these together, because we want to see what happens when we if all of this will add to 1, because it should add to 1, because we've got the probability of a success plus a failure should equal 1. So all of those possibilities should equal 1. And the reason why all of those probabilities together should equal 1 is because we're taking a look at all the possible outcomes that could occur. So if we look at these, I think we've seen this sort of pattern before. So 1/3, well, there's another way to get a third cubed is we multiply a third cubed, there's the failure, multiplied by 2/3 to the power 0, because that's just 1. And then if we're choosing this 1 time, this can only happen 1 time, then we've got 3 choose 0. Okay, and 3 choose 0 is 1. Then if we were to continue along and take a look at the other possibilities when we're only succeeding 1 time, so the shaded section comes up 1 time when the arrow lands on the shaded section once, the probability is 2/3, but that's only occurring 1 time. The failures occur 2 times, and that possibility comes up 3 times, which if we're choosing, it's 3 choose 1. Okay, so that gives us the 3 outcome. And then if we choose, again, looking at combinations notation, 3 choose 2 gives us the value of 3, and the 2 successes this time is 2/3 squared, and then 1/3 to the power 1 will give us that outcome. And we can calculate all these together. I just haven't got all these values written down here. So we'll put all the values here, and then when it's successful 3 times, then we can just say 3 choose 3. That only happens 1 time, and the successes occur 3 times, and the failures occur 0 times. So if we write down all those probabilities together and add them together, that definitely should equal 1. Okay, so if we take a look at all of this together and we summarize it, this is all to suggest that 3 choose some value x is equal to 2/3 to the exponent x multiplied by 1/3 3 minus x to the exponent 3 minus x. So then we're going to then add all these together, so we can substitute in the different values of x that we have here, 0, 1, 2, and 3. We substitute them in, add them all together, and we will see that this will equal 1. And notice that this is actually the binomial expansion for this, and 1/3 plus 2/3 does equal 1, and 1 cubed equals 1. Okay, so that is how all of this is kind of being brought together. So the binomial expansion, that short form of doing it that we learned recently, that is the way to find the probabilities of binomial distribution. So just to summarize, if we're trying to find the probability distribution of some random variable x when it equals r, it's just going to be n choose r multiplied by the success to the exponent r multiplied by the failure, 1 minus p, to the exponent n minus r, and r will equal to 0, 1, 2, etc. up to n. Okay, so r is going to be the number of successes, n is the number of trials, and p is the probability of success, and 1 minus p is the probability of failure. This is called the binomial probability distribution function. So this thing is the binomial probability distribution function. And when we're dealing with the parameters n and p, when we're dealing with our probabilities and our number of trials, if we're looking at some sort of experiment, we can write this as x is distributed as the binomial probability where there are n trials with some probability of success. Okay, so that's how we will see that sometimes written. And of course, this falls into the expected or mean outcome of the experiment. The expected outcome, mu, as we saw last day, is just n multiplied by p. So the number of trials multiplied by the possibility or the probability of success gives us the expected outcome, which is the mean outcome of the experiment. Speaking of mean, as you know, so I just mentioned that, the mean of x is mu. So mean of this outcome is mu, which equals np. The standard deviation of x is sigma, which equals np multiplied by 1 minus p, and the square root of that. So this is the standard deviation of that. So it's the mean multiplied by the probability of the failure. And then of course the variance is just sigma squared, which is just np 1 minus p. Okay, so those are the few little extra calculations that we can make when dealing with binomial random variables. Okay, and of course that's when we are talking about x distributed as a binomial experiment of n trials with probability of success p. Okay, so we're going to take a look at some examples tomorrow, and we're going to hopefully help you understand things a little bit better as we go. So while you're going through the after you finish the video, of course, please go in your textbook and look at example 8 on page 620. Then look at practice exercises 2, 3, and 5 on page 621. Then what we're going to do is take a look at example 9 on page 622. And then I'd like you to look at pages 622 to 623, exercises 1, 3, 5, 7 to 9, 11, and 12. And then look at examples 10 and 11 on page 625, followed by looking at exercises 1 to 4 on page 625 and 626. Okay, as always, you'll have time in class to work on these, but it's always good to kind of familiarize yourself with the work, what works is to come. And this concludes chapter 23. So thanks for watching, and we'll see you in class.